Okay, well, thank you everyone for being here. Today um, Juliusz and I are going to be presenting some work of ours on the EHT and robustness. So I'll let Juliusz get the slides going. He's going to start us off.
Yep.
And then we'll have a quick switch halfway through. So yeah, Juliusz, whenever you're ready, take it away.
Yes, thank you. Thank you all for showing up. I know that some of you may be sort of tired of looking at my face during this seminar series, but really this is joint work, and the fact that you're seeing me here is where Jamie is to be blamed for this, because yeah, as I said, this is joint work, and I'm just going to say a few things in the introduction, and then Jamie will take over for the sort of more substantial part of this talk. So we're going to be talking about robustness and the Event Horizon Telescope. So of course, we all know and love this image of the central object in M87. And today, what we would like to do is sort of look a bit at the epistemology or the possible epistemology behind that image. And in more detail, this is the plan of the talk. First of all, we're going to frame this in terms of peculiar epistemic character of large experiments, or what I guess one could call a particular form of big science. And then I'm going to add a bit about radio astronomy specific challenges, epistemic challenges, and then Jamie will take over to talk about robustness and how robustness could issues concerned related to robustness play out in the context of the image that we all know and love. And there may be a slight bonus about recent EHT papers about polarization, if we have enough time. Good. So, I think some of the epistemological issues concerning the Event Horizon Telescope could be put into a perhaps interesting context of what we decided to call large experiments. So some experiments, in particular in fundamental physics, but of course not exclusively, involve large size instruments, large budgets, large groups of people, unique locations, and or cutting edge science. And what we think of as large experiments will typically have most of these features. Not all of them will have all of those features. Some of them do not need to have unique locations, and some of them may be not so cutting edge, but experiments such as experiments run at the Large Hadron Collider or the LIGO-Virgo-Cagra network have most of those features. And what's interesting about those experiments is that they tend to be sort of, for all practical purposes, unique, because an independent test of the outcome is very often not available. And so in that sense, large experiments have kind of peculiar epistemic character. On the plus side, they provide empirical data, which we simply cannot collect or cannot obtain using smaller setups. And because they are very often a collective effort, individual biases of particular experimenters can be expected to be somehow minimized because the outcome of experiment represents consensus of a larger group. And so in that sense, we should perhaps trust this more than sort of a single experimenter doing his, let's say, I don't know, gravitational wave experiments using bars in their garage. But on the flip side, one could worry that, well, even if a second run of an experiment was possible, a replication of an outcome would be just more data from the same instrument collected by a very similar group of people. And that intuitively seems very unlike a confirmation of an outcome coming from another experiment using different instrument. Because in principle, there could be, I don't know, something wrong with the particular instrument that I'm using. So to sort of paraphrase a quote from Nancy Cartwright, and the quote will also show up in later part, if we had a second run of the same experiment, we would be doing the same thing in the same way twice. And that's, again, very different from a second independent test of a given effect. And all of this assumes that a second run is possible, but very often a second run of the same thing may not even be easily available, simply because you don't have enough, for instance, observational time on the appropriate telescopes, or your device may be decommissioned. And naturally, the Event Horizon telescope is an instance of a large experiment in our sense, because it's a virtual telescope that spans nearly full diameter of the Earth. I'm just quoting the EHT collaboration. And some members of the collaboration in another paper called it the highest resolution imaging instrument in the history of astronomy. And so it's a fairly unique cutting edge science, very large size instrument. And so philosophically speaking, I think it's interesting to see what goes into, or what could plausibly go into trust of the outcome and epistemic warrant of the outcome. So that's the sort of general story into which we think the Event Horizon Telescope is nicely fitting. And now let me talk briefly about some of the issues that one encounters in radio astronomy more generally, but with an eye towards the EHT results. So this is just a sort of brief reminder so that we're all on the same page. In radio astronomy, we're interested in recovering brightness of the source, and we have measurements of what is commonly called the UV plane of the UV plane, and the visibility function in the UV plane is related to the intensity distribution by a Fourier transform. And if we have radio telescopes, we have at best, if the baselines do not overlap too much, so many different baselines. And so a finite and small amount of points in the UV plane are sampled. And sometimes a less sparsing sample is possible, for instance, when the Earth rotation is taken into account, which is what gives us those sweeps in the UV plane that we can see in this picture, which is taken from, I think, paper 1 of the EHT collaboration. So in radio astronomy, we very often deal with data which sparsely sample sources of interest. So that's the first sort of epistemic problem radio astronomy has to deal with. The second has to do with noise, because the visibility measurements in the UV plane are influenced by various types of noise, including various forms of scattering in the solar wind or in the Earth's ionosphere, various forms of atmospheric noise and noise internal to the components of antenna. Yeah, if we go to shorter wavelengths, which we need to do in order to get the resolution allowing for things such as resolving the structure in the vicinity of a candidate for a supermassive black hole, we get even more challenges related to different forms of noise. So a sort of consequence of these two things is that in general, image reconstruction from sparse noisy data is not a Wells problem. And a form of underdetermination arises because multiple images are even compatible with the collected data. And so if you have a sort of large cutting edge unique experiment, this sort of difficulties related to image reconstruction kind of amplify the worries that one could in principle have about the reliability of the outcome. And because this will be sort of useful in section 3, I'm just going to sort of briefly remind us about two main imaging approaches, or at least the two main approaches that the Event Horizon Telescope collaboration used in their analysis of the data. So we have a class of imaging algorithms known as CLEAN. That's a sort of standard approach to interpretation of data in radio astronomy. And this is an iterative procedure. We find the response to a point source, subtract that from the highest intensity point the data, replace that with a particular function, continue until all points above a certain threshold have been removed, and then kind of blend those with a particular other function, typically some certain Gaussian distribution, add the residuals, and all of this gives us some representation of extended structures. The problems with CLEAN are that there are first many variants of CLEAN, the possibility of spurious structures arising, and the procedure being nonlinear, although sufficient conditions under which successive applications converge are known to some extent. And the second data analysis or imaging approach that the EHT use are applications of the so-called regularized maximum likelihood techniques. So the aim there is to find an image that minimizes the objective function, which is a total of how good the data fit minus total sum of some regularization terms. The subjective function is often interpreted as the likelihood of a posterior probability. And different regularization terms may favor different aspects of an image. For instance, in the context of the EHT, some versions of RML methods use favor piecewise smooth images, and some other favor overall smooth images. And the user input for this consists of a decision of which data to use and what regularizer terms to use and what weights those terms get. The upshot of this is that both CLEAN and RML are in principle sensitive to various choices made in the process, and thus are potentially susceptible to being influenced by biases of the user. This makes it, to put it in the words of the EHT collaboration, difficult to assess what image properties are reliable from a given imaging method. So I think this is prima facie sort of epistemic situation we are dealing with in the context of large experiments in radio astronomy. So you may wonder, hey, Juliusz, why should we trust the results? And I'm not going to tell you that, but hand over to Jamie.
Okay, well, let me share my screen. I should, okay, hopefully you can see that. So yes, as Juliusz just said, the nature of the imaging is such that there's this concern about what features of the image you can actually trust if it's just based on one image or one imaging method. And so a natural sort of place to go here is to talk about robustness, which has really recently received a lot of philosophical attention, especially in the context of climate modeling. Let's see if it's, oh, I'm going to have to swap between my screens here. It's not letting me do this. This worked fine when I tested it before, but apparently not right now. There we go. Okay, so the basic idea of robustness is that the convergence of results based on sort of varied evidence leads to robust conclusions, which enjoy sort of greater trust than if they were based on a single piece of evidence. So if we think about an evidence claim of the form, E is evidence for C, any sort of evidence claim will typically depend on a range of auxiliary assumptions, and the fallibility of those assumptions can lead to a failure of the evidence claim or undermine confidence in the conclusion. Now, in the case of when we have a variety of pieces of evidence depending on different sets of auxiliary conditions, then because you're basically got two independent arguments for the same conclusion, depending on different auxiliary conditions, the idea is that gives us extra confidence in the conclusion, because you'd have to have different auxiliary conditions and each of the arguments failing independently. So for robustness, what we want is convergence in conclusions that isn't attributable to an overlap in auxiliary assumptions between the two sort of lines of evidence. And robustness arguments essentially weaken the dependence of the conclusion on any particular auxiliary assumptions or particular set of auxiliary assumptions. Now, this makes it an appealing kind of thing to use in astrophysics. So some sort of epistemic features of astrophysics, of course, there's model dependence for any kind of observation or inference you're making. To some extent, this is true of experiments in general, but it's something that gets worried about a lot in the context of astrophysics. This leads to sort of underdetermination when there's multiple models that are compatible with observations. Another sort of challenge is the long timescales typically associated with evolution for typical targets. Now, black holes in LIGO and DHT are arguably a sort of counterexample to this generalization. And the big problem is that there's a lack of controlled experiments that one can do. One can't go and set up a target system with special initial conditions and observe its evolution in the same way that you might do in a lab. And this at least presents a challenge for the kind of methodology you employ in order to sort of confirm results or inferences from observations. So in general, inferences depend on many auxiliary assumptions. And in astrophysics, a lot of the typical experimental methods you might have for justifying those confidence in those assumptions might be unavailable or at least sort of difficult in astrophysical contexts. Now, for the EHT in particular, it's clear that sort of systematic variation in the experimental setup of the kind that you might have if you were setting up a separate experiment is just not going to be a viable option. We're probably not going to have two telescopes the size of the Earth, two completely separate and independent arrays. Rather, the data gathered by the EHT provides essentially a unique line of evidence about the horizon scale structure of M87 star. So two questions arise. In what sense, if any, are the arguments that the EHT is making, in what sense are these robustness arguments? And is there a sort of a philosophical account of robustness according to which we can sort of say that these arguments are indeed good ones? And note here that in robustness literature, the value of robustness, the epistemic value of robustness across variation in experiments is more or less agreed upon, whereas the epistemic value of robustness across variation in models or modeling assumptions is more controversial. Okay, so here's sort of a classic example of this. So Cartwright talks about reproducibility. This is where you have variations in methods and data, essentially doing a new experiment rather than replicating the same old experiment. And this enables a kind of argument from coincidence. The idea is that it would really be a coincidence if each of your separate methods independently produced the same wrong result. They would have to fail separately and for different reasons, and this would be a real coincidence. And so here, Cartwright reflects the broad consensus that robustness across variation in experiments increases the security of an inference or evidence claim. On the other hand, Cartwright is puzzled by robustness arguments where the variation is to do with the implementation of a model. So she says, for the different implementations do not constitute independent instruments for doing different things, but rather different ways of doing the same thing. Instead of being unrelated, they are often alternatives to one another, sometimes even contradictory. And so we look at the phenomenon with, at the very most, one instrument which could be operating properly. So the idea here is that at best, one of your models is sort of like the best one, it's the correct one. And variation in your modeling assumptions is going to make these alternatives inconsistent or with the sort of best model that you have. And therefore, it doesn't do anything to sort of raise confidence in your conclusion if you have an ensemble of contradictory or alternative models giving you the same answer, because the correct model might in fact give you a different answer. Now, the chair has recently argued against this argument, basically on the basis that it relies on a faulty picture of the epistemic roles of models in confirmation. So I'm going to give a quick gloss of this argument, which is basically that the point of a model in these kinds of confirmation contexts is not to be true or like a completely accurate representation, but rather to be a reliable inferential tool. So a model doesn't need to have all true assumptions in order to be reliable for a given purpose within a given domain. That is to say, there's an analogy here between models and sort of normal experimental instruments in their use in a measuring process or in confirmation, empirical confirmation. So inconsistent models can indeed be reliable tools for the same task, false models or models that are inconsistent with each other. And so the chair argues for a unified account of robustness that treats variation across models and variation across experiments or experimental instruments in the same way. It treats them all in terms of the auxiliary conditions that are required to be true in order for the conclusion to be false, in order for the conclusion to be justified, sorry. Another recent account of robustness comes from Staley, who in this 2020 paper offers an account of a situation that is of particular interest for us. So Staley considers robustness analyses where the models are being varied within a particular measurement context in order to account for systematic uncertainty. So the idea here is that alternating the models or the modeling assumptions used in a particular measurement, where measurements are being understood as model-based inferences, this leads to a kind of ensemble of measurements using these different modeling assumptions. So you've only done sort of one physical measurement and gotten one set of data, but by making inferences based on sort of a range of models, you get sort of different, a range of effective measurements. And then he says that experimenters can employ a kind of weakening strategy where, guided by this robustness analysis that reflects the sort of ignorance of the experimenter, one can report a weakened conclusion that's sort of secured by this robustness analysis and reported in terms of systematic uncertainty. And I'll also note here that Staley offers a far broader account of the many ways that robustness can increase the security of an evidence claim in this 2004 paper. Now for an example that sort of illustrates the significant importance of robustness. So of course, the infamous bicep 2 retraction. This sort of demonstrates the importance of establishing sufficient robustness at the data analysis stage as part of astrophysical methodology, we think. So just a very brief recap of this story here. The initial claim from coming out of bicep 2 was that they detected gravitational waves through this detection of the B mode polarization in the CMB. Of course, these B modes can be caused by a range of sources, including the lensing of galaxies and by dust. And so those effects needed to be subtracted in order to make the discovery claim. Now, the Planck data came out and showed that the bicep 2 modeling of the dust contribution was inadequate. They hadn't taken account of sufficient range of modeling assumptions in their analysis. And it turned out that the dust contribution could account for the whole of the gravitational wave signal. So this is a kind of cautionary tale to astrophysicists. It shows sort of how crucial it is to demonstrate the robustness of a result across a range of auxiliary assumptions in order to secure the claim against the failure of some of those assumptions. Now, in this case, of course, there was alternative data in order to that was able to sort of shine light on this being a problem. But this becomes the sort of need for robustness in considering a range of modeling assumptions becomes particularly important in cases where no alternative data is available. Okay, so now to the 2019 EHT images. So robustness plays an explicit and important part of the justification that's actually being provided by the EHT collaboration in their papers. So I think this is from paper 1. A number of elements reinforce the robustness of our image and the conclusion that it is consistent with the shadow of a black hole as predicted by GR. First, our analysis has used multiple independent calibration and imaging techniques, as well as 4 independent data sets taken over 4 different days in 2 separate frequency bands. And they go on to list a number of other considerations that add to the robustness. Here's a non-exhaustive list of all the various elements that are contributing to the robustness. So we have the multiple data sets over different days, the measurements in different frequency bands, multiple calibration pipelines discussed in paper 3. What we'll be focusing on today, the multiple imaging pipelines, both at 2 different stages of the imaging process. This involves multiple imaging approaches, so clean and RML, as Juliusz discussed earlier. Multiple algorithms that implement these, including EHT imaging, SMILey, and DiffMap, and also multiple imaging groups. So actual different groups of humans working independently and not talking to each other. There's also a historical aspect to robustness, the sort of gradual improvement of the array over time. So 2009, pre-HT array had 3 stations. 2017 array had 8, of which 7 could actually observe M87 star. Okay, so just going to talk now, focus on the 2 imaging stages that get discussed in paper 4. So as we've said, clean and RML methods are susceptible to influences by biases of the user. They require expert input, and at least there's the worry there that biases of the user, sort of their expectations, could end up biasing the image depending on what inputs they use. And so stage 1 of the imaging was really aimed at overcoming this problem. So independent imaging pipelines were set up where they weren't talking to each other in order to protect against the worries of false confidence and collective confirmation bias, essentially stop a kind of group think process by which they came to sort of consensus or agreement that reflected sort of biases from talking to each other and ending up agreeing with one another. Having 4 independent pipelines that independently came to sort of robust conclusions, that's taken to indicate that something's going right. So you can see these 4 images. They're not, I mean, visually in some ways they're quite different, but they do have certain stable features. And so the initial blind imaging stage indicated that the image of M87 star is dominated by a 40 microsecond ring, and the ring persists across the different imaging methods. So here we have an identification of the features that are stable or robust across the different pipelines, and those are taken to be trustworthy, to at least to some extent. Now, stage 2 imaging, which happens once they've all gotten together and are talking to each other again. The goal here was then to explore the dependence of the reconstructed images on different imaging assumptions. So this involves using the different imaging methods, clean and RML, which of course were both used in the previous step, but here it's a sort of a more systematic consideration of the effects of those choices. And 3 different algorithms. Each of those require user input, but importantly, the sort of interpretation and numerical expression of those inputs differs across the methods. So it's sort of not the case that you're just putting in the sort of same assumptions you're not making the exact same choices or assumptions when you or applying those different imaging methods. And this step also involved variation in the parameters that are used for each algorithms, these sort of inputs. And these were sort of determined by parameter surveys, where the acceptable parameter combinations were determined by testing the algorithms on synthetic data sets. So what's happening here is that we have 4 simple geometric models: the ring, crescent, disk, and double. Starting with the geometric models, synthetic data sets were generated from each of them, representing what the EHT would have observed if looking at such a source. And then for a range of different parameters, each of the algorithms was then used to try and reconstruct the image based on that synthetic data set. And so taking the algorithm and plugging in a bunch of different parameters and seeing how well the algorithm functions for each of those parameters, you can see which parameters are the good ones to actually use for imaging. And note that these geometric models are all at least sort of roughly consistent with the EHT data, but are all quite different. So part of the idea behind this step is that the algorithm has to be able to work for at least for a range of different models or systems that would be roughly compatible with the data. Okay, so they say our surveys are coarse-grained and don't completely explore the choices in the imaging process. Nevertheless, they identify regions of imaging parameter space that consistently produce faithful image reconstructions on synthetic data, and they help us identify which features of our reconstructions are consistent and which features vary with specific parameter choices. So here, very clearly, a robustness argument. Those features that are consistently reproduced by the algorithms for a range of input parameters are to be trusted. Those that are very dependent on the parameter inputs you put in aren't to be trusted to the same extent. So certain features of the image are robust, others not. Okay, then once you have figured out which parameters are the good ones, so identify the fiducial parameters, which is the unique set of parameters that causes the algorithms to function the best, but also the top set, which is the sort of full range of parameters that produces sort of acceptable reconstructions of the images, the synthetic images. Having identified those sort of best parameters, the fiducial parameters are then used to produce fiducial images for each day of the data taking and for each algorithm. So that's that first table there. And yeah, apologies for the very non-sophisticated image that I've used in a talk that's all about sophisticated images. Okay, so as we can see this, I don't know if you can see my cursor, but the April 11th, great. The April 11th images from each of the algorithms were then blurred to conservative resolution. And then finally, the sort of simple average across the 3 algorithms was taken in order to produce a single conservative image for that day. So at the first step, you can see that there are certain features that are consistent across all the images. These are sort of those that are considered to be robust. When we get to the blurring to a common conservative resolution, I think this arguably is a kind of weakening strategy, like the kind that Staley discusses, where the precision of some of the images is sacrificed in order to bolster the security or the confidence in the claims being made. And this reflects a concern with robustness, because essentially what's being said is that the more fine-grained features, perhaps, of the higher resolution images based on the RML, those cannot necessarily be trusted if similar features aren't to be found in the clean images. We want robust features across all of the algorithms in order for us to really have trust in them. I think there are some interesting things to be said about the sort of nature of this final product, the simple average across the different algorithms. There's certainly some kind of, and as Peter I know has talked about, there are some sort of social elements to this, but also they sort of represent. There's sort of a nice way of representing the analysis that you would do across the multiple images. They sort of summarize or represent the robust features across all of them in a way. The fact that it looks like the other three, it's some kind of indication that it's representative. Okay, so before we conclude, we should talk about what, to my knowledge at least, is the sort of only other sort of philosophical take on these issues in the literature. So Weinstein in particular adapts Cartwright's argument mentioned above in order to argue against, seemingly to argue against the value of the robustness in the EHT imaging case. So I'm quoting Weinstein here. She says, since the results are very robust, says Cartwright, we think that there must be some truth in them, but she, here being sort of an imaginary Cartwright, disagrees with this claim. And that's because at the very best, one and only one of these assumptions can be right. We may look at the images produced by the 3 imaging pipelines, but pipeline number 4 may generate an image with no shadow at all. If God's function, that is, I guess, the sort of correct one, is this fourth pipeline, is in the 4th pipeline, then the 3 other imaging pipelines, which is just nothing. And so the imaging pipelines are uncorrelated with the general argument because their output image has no bearing on what images in the 4th, 5th, or 6th pipelines would reconstruct. So here what we're getting is an application of Cartwright's sort of skepticism about robustness across modeling assumptions, as mentioned earlier. So this argument rests on the following claims. First, that the imaging algorithms are alternative and possibly inconsistent models of the kind that Cartwright's arguing against. And second, that when we have such alternatives, at most one of them is able to be a reliable epistemic guide. And so robustness across variation in these alternatives offers no further sort of epistemic value. Now, against the second point, I've already mentioned Dechair's argument that even in the case where models have false or idealized assumptions, they can still nonetheless be reliable tools for a given purpose within a given domain. And so we shouldn't necessarily think, accept that alternative models, because they're not all true, are going to fail to provide the kind of robustness being offered by the EHT. And second, the Staley example shows how varying model assumptions to represent sort of experimenters' ignorance about those assumptions is a form of robustness analysis that does increase the security of the conclusion, admittedly at perhaps the cost of precision of the actual claim being made. And now against one, it seems that even if we reject the analogous treatment of models and instruments as argued for by Dechair, nonetheless, imaging algorithms could still be analogous to instruments because they sort of represent a middle ground between representational models and sort of physical, alternative physical instruments. So often the robustness literature is concerned with climate models, but these do not seem to be analogous to the kind of models that are causing concern in that context. So the imaging algorithms aren't representing a target system. They're not sort of representational models. There's no sort of, nowhere in the algorithm you can point to that's representing a feature of the target. So it's not exactly clear how these algorithms are supposed to be false or inconsistent with one another in the way that is sort of needed for the Cartwright argument. And also insofar as they do produce convergent results, it seems that these are tools that are successfully reproducing a phenomenon in Cartwright's sense. They really seem to be reproducing, they seem to be providing sort of alternate, sort of virtual experiments, and acting much more like the physical tools in an experiment than a representational model. So even if models, variation in models doesn't require robustness, we could still think that variation in these kinds of algorithms provides the right kind of robustness. Okay, so conclusions. The 2019 EHT image of M87 star, we think should be understood as robust across variation in a range of auxiliary conditions, including various imaging pipelines, yes, and a whole range of other things that we've talked about. Now, not all accounts of robustness are going to be able to make sense of the trust that we should purportedly have in the EHT conclusions, but at least some seem to. And finally, the case of the EHT underscores the importance of robustness arguments in astrophysics, especially as a case of like a large experiment where alternative experimental runs are not necessarily feasible, but the kind of robustness offered here seems to be important in those kinds of situations. Okay, well, I think we're pretty much out of time, but if people have questions about the Q&A, in the Q&A about polarization, just we do think that these kinds of arguments will carry over to the what's being done in papers 7 and 8. So.
Okay, that's wonderful. Thank you very much for a beautiful talk, guys.
Shall I stop screen share?
Jamie, would you rather I stop the recording, or would you like to record the questions as well?
I think we typically record the questions.
Yeah, but I'm just, you okay with that? Yeah.
Yeah, as long as nobody's planning on.
Okay, no, just
figure out how stupid everything we've said is.
Just asking. All right.
We can always cut it out later if it gets too gruesome.
Sure.
Okay, I'm just gonna stop that.
So let's see, we have some raised hands. So let's start with Peter.
So you'll not be surprised I have thoughts about this topic, and some of which we can go over, Juliusz and Jamie, offline. But a couple of comments. One is that on the role of the large experiment as opposed to the general experiment and observation. Back when dinosaurs ruled the earth, I wrote a book, How Experiments End. And one of the things that I found there, I was looking at high energy physics, not astronomy, was that many of the dynamics of the scientific community, more largely construed, take place inside a large scale collaboration. And so things like internal refereeing, publication decisions, decisions about what a valid result is, and so on, are internal. And some of that is because a large fraction of the community is involved in the work, and some of it is because only an experiment with hundreds or thousands of people know some of the grimmest details of what's going on to be able to do that. It doesn't eliminate the role of external refereeing and external probing of the vertical structure of what's being put forward, but that's also true in the EHT. And there's a very strong role for a whole range of testing that goes on inside at the level of review, and we have these data analysis reviews, we have internal refereeing through many rounds. So by the time it goes to the external community for refereeing, it's been through a lot. And publication decisions and authorial structure and so on. Much of this goes on inside. And so I think there is a role. I think it's important to recognize that a big experiment, and at the time of the 2019 publication, I think we were 207 authors or something close, plus or minus a few. And now it's about 400. I think in 5-6 years ago, it was about less than 100. So it's grown very rapidly, and that has its own dynamics. The second is it might be useful, might not, but I've pushed on an idea that robustness and stability often are in complementary relationship, and that in order to achieve directness, sorry, not stability and robustness, directness and robustness, or directness and stability, were often complementary, and that in order to get more direct and precise results, you often had to sacrifice the reliability of a robust or stable answer, and conversely, and that trade-off is often used inside the dynamics of experimentation, from one experiment or observation to the next, or even within a set of observations. And perhaps that might be of use because robustness is very important, and for the EHT, as well as experiments like the Large Hadron Collider and so on. But sometimes you want to sacrifice that for a golden event, or a particular, a less stable but more direct and precise result. And there's a back and forth between those. A third comment is about a model. So I don't think there's a right answer to what a model is, but I do think that there's a difference between the way you're using model and the way the EHT uses model. So that's okay if you want to match up with certain literature within the philosophy community, but so for example, the EHT never talks about the difference between RML and clean as different models. We don't do that. And so the use of models in, for instance, establishment of the regularizers, there are different degrees of how hard we push a model onto reduction of data, but there's also the synthetic models that are used in establishing the top set and then the fiducial set of settings. That's a model in the sense that the EHT uses it. Now, again, I'm not saying that the EHT rules once and forever on what counts as a model. I just want to make sure there's no mismatch in vocabulary. So when you see in the papers reference to models, it's different from, I felt that you were pulling in that same direction when later on you talked about tools, for instance, clean versus the regularized likelihood ones. That's more like the way EHT uses those. I think that, so I had this debate for ages with Ian Hacking about the difference between observation and experiment. And at least in high energy physics, if you compare a colliding beam experiment with a astrophysical observation, it seems to me sometimes pretty hard to make a radical distinction between observation and experiment. This for two reasons. First, say you're a member of the ATLAS team, one of the big colliding beam detectors at CERN. You are not in charge of the colliding beam dynamics. That's a completely different group of people with different training, different expertise. They don't answer to ATLAS. There are other detectors on the line. In the Higgs discovery, there were 2, but there are 4 in principle of intersection points. And so what they get is what comes out, the debris from that colliding beam, they then have a lot of control over. That is to say, they can change their muon detector and they can change their hadron detector, their central particle detector. They can look at, there are all sorts of things that they use, but that actually is kind of analogous to what you do in an astrophysical observation. So for example, you can change, you can put polarizing, you can make polarization measurements, you can, look at different sidebands, you can, but you can't, obviously we can't, what Ian Hacking was offended by in astrophysics and about black holes was that you couldn't mess with the astrophysical objects. That's true, but you also can't mess with the individual collisions of protons and antiprotons. And we had this argument forever and a day. He didn't move me, I didn't move him, but I'm not convinced that there's a radical distinction between what goes on at the LHC in terms of the you many powers of 10, I forget how many are in a bunch in the LHC when the protons hit the antiprotons, but you can't tell which proton and antiproton are going to hit. You have zero control over that. And so, you have an average, you figure, their cross section for intersection, and then they hit and they produce a gigantic number of high multiplicity number of particles that come out. And then you try to do things with your detector to try to capture that. I think that's actually closer to observation than the old 17th century distinction between observation and experiment might suggest. And then the last a quick comment for now, and I postpone others to later, on the role of averaging in the image in the EHT. So I have lectures on this that are on YouTube, and you've seen that. And but I think that the key epistemic role, put aside my own view about objectivity and the different forms of argumentation, but just that the key epistemic role for averaging was that it emphasized features that were common and de-emphasized features that were not. Now, it's true, as you mentioned, Jamie, I didn't like, and I still don't like, the argument that we should average to make sure that all the groups felt equally patted on the head, which was an argument that some colleagues made. I just didn't, it's a nice feature, but that didn't persuade me in any way. And I thought it was stupid to rely, well, I should say something more diplomatic. I disagreed with relying that as an argument for why we should average. But the idea that it would emphasize common features and, so for instance, outside the main ring, there are lots of features that are distant, that are far in the field of view. Those differ, those are wildly inconsistent, even within a single method of reduction. And no one in the end, I think, Shep can correct me if he doesn't agree with this. I don't think anybody took too seriously the details of the far out flux that we were seeing, because it was super responsive to very small changes. Whereas the reality of the shadow, the ring, and the brightness in the south, those were features that were robust. So what the averaging did was to de-emphasize the micro variations in the distant field of view flux and to emphasize the things like the increased flux in the south of the ring and the basic shadow size. And so that seemed like a more conservative approach. It seemed to be more conservative, just the way, not super resolving or and able to blurring in a way that felt like it was consistent with the accuracy of the experiment or the precision of the experiment. Those are just some comments, but thank you. I look forward very much to talking more about these things, but the repetition of the community inside the experiment, the complementarity aspect of robustness and directness, the nature of a model and how that term is used, the early modern distinction between observation and experiment, and the role of averaging were the main things that I wanted to bring up.
Well, thanks. That's a lot of really great stuff. I can respond to at least a couple of those things a little bit. First of all, I think you're right that certainly for the purposes of this talk, we haven't really been sufficiently careful in the use of the term model, which is a very slippery word that gets used in every possible different way, seemingly. And so I think we've sort of loosely been talking about variation across modeling assumptions, or in order to sort of make the connection with the robustness literature and sort of bring out the sort of concern I think that arises in terms coming out of that literature about robustness that isn't to do with the actual varying physical experiments. But I certainly agree that it's unnatural to think about the imaging algorithms themselves as models. That's maybe stretching the term a little bit far. And I hope we never quite did that, but because of course, as you saw at the end, we do think that these algorithms are even a better case for being analogous with physical instruments than, say, a representational model is. I think the other thing I would say is that I think so when I'm thinking about the different, you get the fiducial images and then you blur them and then you average them. I guess thinking about this in terms of sort of representation or accurate representation, it seems to me that in a way, these are different ways of presenting the same information, right? That if you look at that top grid of the all of the fiducial images, then sort of properly interpreted, you can get the same robustness information out of those that you get out of perhaps even more information than you get out of the final averaged image. So if you are sort of an expert and you know how the whole process works, then you can look at this range of images and sort of figure out what the robust features are. And you have an image in your own mind of what about this is reliable. And then the sort of blurring to get the more sort of conservative features is in a way implementing what you know if you're an expert, which is that these more fine-grained details maybe can't be trusted as much as the sort of larger features that are common across all of the images. And then again, as you're saying that the averaging, again, it's representing a sort of more conservative, it's emphasizing the things that are the same and de-emphasizing the things that aren't. In a way, people like you, people within the collaboration, in a sense, don't need that step in order to be able to understand which features of the image to be trusted and which aren't. But it is a really nice way of representing the analysis that you've done about what's to be trusted. It's kind of a nice way of being able to just sort of see the uncertainties reflected in the image in a way. I don't know if you would agree with that sort of rephrasing or but
yeah, I think that's we might, if you were inside, if you were thoroughly inside the different approaches, you might say what you really want to do is to understand the vulnerabilities of each technique.
Mm-hmm.
And that's one of the things that I really want to do as we're right now, I'm really trying to do is to, and not just me, others, is like, what is clean exactly vulnerable to? What is Smiley exactly vulnerable to in its imaging? And they're not the same. So there's actually a kind of complicated sort of multi-dimensional set of vulnerabilities here that you can understand that does go beyond averaging and also where it's super reliable. We know there are things that Clean's really good at, point sources, for example. We know that there are things that the RML methods are really good at, and there are other more model dependent methods of imaging that are really good at other things. Yes.
Yeah. And I will say that this kind of brings up, I think, maybe what would be the more charitable or a sort of reinterpretation of the Cartwright argument to apply to this case, which is that there's a sense in which you need to have that deeper understanding of exactly what the vulnerabilities are, and there's no sort of sense in which the sort of three images are a representative sampling of the possibilities of different imaging methods. Like what would that even be? There's not sort of a parameter space of imaging methods that you can sample from. And so it is clear that this kind of, comparing three images, the robustness across this variation is quite a different nature than like variation in models. And insofar as some are better or worse for the task, or better or worse at certain things, averaging kind of doesn't make as much sense as it might if you had some kind of representative sample. That might be that's me trying to put myself in Cartwright's point of view and giving a word. Yeah, trying to worry about this a little bit more. Anyway, I don't know if Juliusz, do you have anything you wanted to add?
Maybe I just add super briefly one thing about the complementarity and the trade-offs. I think one of the sort of things that made me kind of subjectively increase my degree of confidence in the image were multiple points in the paper, where in the EHT papers where the collaboration in principle could have gone with, I don't know, the RML analysis, which seems to give slightly more data, or with particular nice choice of data set, a particular nice of the outcome, but decided not to in order to do what I would and what we in the stock interpreted as going for a more robust conclusion instead of more precise or one. And so in that sense, the trade-offs are sort of out there in the papers, and one can, in many cases, pretty easily spot some of them.
All right, let's have Eric and then Shep. Sorry, Shep, but I think your hand was raised after.
So, Jamie and Juliusz, thank you for that really excellent talk. You know, I think your heart's in the right place, and you know, I generally agree with what you're saying. And you know, if someone wants to beat up on Nancy, I'm almost always on board with that. I will never forgive her for the title "How the Laws of Physics Lie." But a little more seriously, I'm not sure that I buy your claim, because you didn't really give an argument, but your claim that these algorithms can be thought of at least usefully as appropriately or relevantly analogous to tools or instruments. I mean, one of the reasons why we trust an experimental tool, a probe, you know, a measuring device, when we in fact trust it and have good reason to trust it, is generally speaking because of a combination of factors. We have different ways and different tools of probing the exact same systems, and they all return consistent results. We have theoretical models that tell us, for lack of a better word, what the causal mechanism is, that you know, what causal kind of pathway there is from the phenomenon or system we're studying to the result the instrument gives us. And we can test at various points along that causal pathway to make sure that there are no points of failure, or you know, to test for points of failure along the causal pathway. And then we have generally the kinds of theoretical models we have of these causal mechanisms are themselves very well entrenched, based on multiple evidential pathways and being embedded in different evidential networks, independent evidential networks. There's a whole business of kind of justifying why we trust these physical tools that we use in the laboratory. And I just don't see that we have an analog for any of that for these algorithms that you're talking about. So, so instead of telling you that you're wrong, because I'm not sure of that, I would rather like to ask you to say a little bit more about it. If we don't have the kind of, as I claim, we don't have the kind of normal ways for justifying and trusting these analogies when we try to think of them as instruments, what are the reasons that we should trust them?
Well, I mean, I would say that there's direct analogs to all of the kind of ways that we would usually go about testing whether an instrument works. So I know that, well, clean, of course, is very widely used in astrophysics in general. So there's sort of a lot of, there's a long history of, you know, being able to, I think, good reason to trust it on the basis of these other uses. But even just within what the EHT does, I mean, the fact that they consider a whole range of synthetic images, not just those geometric models, but things like Frosty the Snowman, this kind of wide range of images that they consider to see whether their algorithms are capable of operating correctly in a wide variety of sort of imaging contexts. I mean, I think that I'm a bit skeptical about the need to think of this causally, if only because I think that a lot of the instruments that we use, at least we can have trust in them long before we really know how they work. I think microscopes are kind of the standard example here, right? But I think what the EHT does is testing the algorithms along a range of contexts in a way that really grounds counterfactuals, like if we were looking at something different, then the algorithm would have spat out an image that looked quite different. If you use these different algorithms to observe the same image, then they will end up agreeing.
But it's worth pointing out that neither one of those counterfactuals has any bearing on what to me is the most important conditional, that or it's not really conditional, has any bearing on the claim what the image shows us is what the thing really looks like, in some sense, or really looks like. It can be completely true that if we point the EHT at a different object, it will show a different image using these algorithms, and yet that has no bearing at all. That may have no bearing at all. Certainly has no logical bearing, and may have no conceptual bearing on whether or not what is showing us it's looking at is in some relevant sense what we're giving us relevant information about what we're looking at. The fact that it systematically varies doesn't show that it's giving us the right information about what we're looking at.
I mean, there's a sort of additional part to this, which is that the EHT array has been used to observe other sources than the M87, like for instance, some known calibrator sources, and up to a certain degree of accuracy, the sort of, from what I understand, the main imaging approach is in the EHT recovered what for other reasons and using different instruments we already know about the calibrator sources. And so then I think to some extent you could say that this gives us confidence that what we get out of the EHT imaging methods is what the source looks like, insofar as we can recover what we independently think those other sources, like calibrator sources, for instance, look like. And so then in that sense, a sort of recovery of things like, what we know about calibrator sources may give us some confidence that we actually can establish the claim you're asking us to.
Well, I find that a little more convincing, but let me grant for the sake of argument for a moment that y'all are right. Does that mean that I should in fact begin to think of all statistical based methods in science as instruments in the same vein as a microscope? Is students' T rule now? I should think of that as being analogous to a microscope.
Well, we're not saying that you should think of those as being fully analogous. We're just saying here's a particular context where physicists publishing those papers could be interpreted as treating them as somewhat analogous for a particular purpose, which is establishing robustness of a conclusion. This does not mean that the same thing happens in other cases.
Yeah, I would think
it's rather, this is an argumentative strategy that is being used in this particular case, in this particular context, and it may fail in other contexts.
I also just want to say, I think I would push back a bit on the sort of, you seem to be sort of straying into things like what the source actually looks like. And I'm not sure that really makes sense when we're talking about, first of all, this kind of frequency, which I don't think there is an answer to the question what this really looks like. I mean, with human eyes, of course, it's not going to look like what we're measuring with a radio interferometer. So these are representations, and they have to be accurate representations for a particular purpose. And with the EHT, that's going to be things like inferences about the mass of the black hole, or whatever further physics you want to do from there. And moving on, once we start looking at those inferences, I think you start having connections with other aspects of astronomy, other observational methods. For something like the mass, you do have this other kind of robustness that involves different experiments where you can confirm that these are actually reliable guides for inferences, at least to some extent. And so to me, that's the kind of accuracy that we're looking for. There's no sort of fact of the matter as to whether this is what the black hole looks like.
So I think you're exactly right, which is why you may have noticed in the middle of asking the question, I kind of caught myself and changed from what it really looked like to giving us the relevant information. But no, I think you're exactly right. And I have to say, I find what both of you just said a lot more convincing than what you said in the talk. So thank you.
Mm-hmm. Thank you.
Thanks.
All right. So Shep, please go ahead.
All right, thanks. This is very interesting stuff, and I come at this from the perspective of a little bit of an outsider or a practitioner.
Anyway,
but but I find it very, very interesting. I'm going to add one other thing. Everything that's been said is very germane, and we wrestle with all these things. I think Peter put it very well, and Eric raised some good questions. I also want to point out that Jeremy Steger's on the line. He was an RU student who worked with us at Haystack Observatory many moons ago. So welcome, Jeremy. I think you've made the leap also into history of science and maybe even philosophy too. So it's great to see you.
To you as well. I didn't know if you'd remember me, but yeah, it's great to see you.
Oh, absolutely, absolutely. It's wonderful to see you again. And so I just want to raise a slightly different point. I'm very much a long game kind of person. And I really do see the Event Horizon Telescope as a compact between the practitioners of today and Einstein and Schwarzschild, Hawking, Wheeler, this entire historical narrative, because it also speaks to how we come to understand the reality of things. Ideas do not come fully formed. Rarely do they come fully formed. And the acceptance of something in the science is a gradual process. And we have to, it's like a roast in the oven. I mean, you kind of have to wait. You can't rush a roast, right? You have to wait for it, right? And the ultimate acceptance of the EHT results may require some annealing. And do you mind if I show a quick slide? Can I share my screen very quickly? Would that be okay?
That's absolutely fine. But yeah, you're co-host now.
Okay, here, I'm just going to show you something very quickly, which kind of a touchstone. So these are 4 different views of Cygnus A. And the upper left here is what Cygnus A looked like according to astronomers in 1953 when they first used closure phase. And I think Jamie and Juliusz have talked about phase a little bit. All we knew was that there were these 2 shoe boxes on the sky, separated by this amount. And then when you had Earth rotation aperture synthesis at a higher frequency, the Cambridge 1 mile telescope showed us even more detail. Consistent roughly with what we saw here, but we're building on it. And then the Cambridge 5 kilometer telescope at 5 gigahertz with 8 elements. Amazing for its time. People were like, agog. You see these lobes, and you can clearly see the impact on the intergalactic medium with the central source here powering it. And then, of course, you go to the VLA with 27 dishes, 20 kilometer baselines, and you get this just astounding picture of something. But there is this robustness that's derived from prediction and the meeting of those predictive elements. And so I just wanted to introduce that as a measure of robustness, being able to predict something, seeing with the next group of measurements that you recover that, and then moving on from there. So as we build out the EHT, as we take better data with more telescopes, which even now we're going to do next week, this is part of a long process, and we expect that we'll start to see things that will corroborate the past. And if you have a result and you can't say next what you expect, or you say the only way to test this is with a device made of unobtainium, then that's a problem from my humble astronomer perspective, but we're taking the right steps here with the EHT and making predictions that we can test. Just wanted to add that. Thanks.
Juliusz, did you want to say anything? Or
No, thanks. That's a beautiful example of. So at some point, I think we said that part of the trust that you folks seem to have in the EHT comes from the fact that you had those really tiny arrays. Well, not really tiny, but like arrays with few. They were still huge, but arrays with few elements, and that seemed to be working well. And that gave you a sort of confidence that you can go and build larger and larger ones. And that seems to be an example, sort of going in the same direction. That's all I would like to add to this beautiful example.
Eric had
Unless Jamie wants
Eric
to add
has a
something, then Eric, go for it.
Yeah.
So, Shep, I was wondering if you could just say a little more about what exactly. So I thought that your remarks on prediction were really spot on. I totally agree with that. I was wondering if you could say a little more about where you think that this kind of big experiment astronomy in general is where it can go with regard to prediction in the near future. What kind of predictions do you think we can make that we can use to get the kind of epistemic entrenchment that we want?
That's interesting. I'm not quite sure if we'll ever get to this mythical goal of knowing for sure, because of course, as Jamie and Juliusz said, we can't go to M87, at least not yet, and we can't really see with our eyes, whatever that means. So we're always grappling a bit in the dark. It's not like an MRI. With an MRI, you have imperfect data, but you could, with surgery, verify what's going on inside the human body. You can take an X-ray, you don't know for sure, but you could do an autopsy and see what's going on. We can never do that with astronomy, but we can make successive predictions that are resolved, and that does increase our confidence. So you ask about what we can do. So for example, as we get more telescopes, in the next week we'll be observing with 11 telescopes as opposed to 8 telescopes. We would expect to see a refinement of the kinds of images that we see. We would expect to see that the slight variations over time that we've noticed and just commented on briefly in the first papers come into focus, and we can study those a little bit more. And we might say that the predictions that we have based on the simulations that we run, seeded by these first observations, make sense in this global confluence of simulation and observation. And then I think something that Juliusz said is very important. We look at calibrator sources, and we want to refine those as well, and start to make very much the link between the small scale and the large scale. As a concrete example, in the M87 image, one of the bedeviling things is that we do not see the large scale jet. And I think Peter mentioned something about the large scale flux. And we said, oh, well, we're not going to worry about that just yet. We really have to worry about that now, okay? Because we know that at 3 millimeter wavelength and 7 millimeter wavelength, we see this amazing jet that goes off, right? And we know the direction of the jet and the opening angle of the jet, and the power in the jet, and the flux density of the jet, and the spectral evolution of the jet. And these are all, you can tick these all off, and you better match all these things, right? And because of the dynamic range limitation of the EHT right now, we can't make that link. With the new dishes, much higher dynamic range and baseline length, going down to the smaller baseline lengths, will recover that low surface brightness jet, and it will match up at some level with what we see, and it had better match up. So that's a very clear prediction that from the small detailed high brightness scale to the low surface brightness linked to the jet, that has to tell a consistent story. And I think that's a very powerful prediction that would bolster confidence. again, it's this annealing over time that we all rely on. That's
Thank
an
you. That's-
imperfect answer to an imperfect problem.
That's really helpful. Thank you.
All right. Well, are there any more questions or fingers?
Great talk. Thank you both.
Yeah,
Thank
really
you.
interesting. Thank you.
Thank you, Juliusz and Jamie again.
Thanks for coming. Thanks.